So we define negative of a contour. So contour C, we define minus C. Now similarly we want to define addition of two contours. That is, suppose if we have a contour C, C1, which is given by Z1t and on interval A to C. And C2 is a contour which is Z2t on C to B. So A less equal C, C less equal B. And these functions Z1 and Z2 are so that they coincide at point C, because see, Z1 is also defined on A to C, Z2 is also defined on C to B. So both Z1 and Z2 are defined on C. Okay. Both Z1 and Z2 are defined on C. Therefore, we want Z1C equal to Z2C. Okay. Then from A to B, we have this function which is given by Z2 on the part A to C. So this interval, if you look at A, C and B, then on this part you have Z1 and this part you have suppose Z2. Then this entire curve which is given on A to B is called addition of C1 and C2. Is this clear? So this curve is Z1, this curve is Z2, then this curve which is traced by putting both, this is juxtaposition one after the other, then this is C1 plus C2. So read the definition now. Let C1 be the contour given by Z1t, A less equal T less equal C, and C2 be the contour given by Z2t, where C less equal T less equal B, with Z1C equal to Z2C. Then the contour C given by ZT on AB, that is on the entire interval AB. Show that part. So Z1C equal to Z2C and on entire interval AB such that Z equal to Z1 on the part AC and Z equal to Z2 on part BC, that is C to B. Then this curve is defined as C1 plus C2. Simple example could be in the plane, suppose if you have this point and then you have this straight line and then there is again straight line. So this curve is C1 and this curve is C2, then this curve is C1 plus C2, that is traversed from this to this. This entire thing can also be looked upon as a curve, and that is addition of these two curves, because first curve and second curve, they match at this point. So the first curve ends at the point where the second curve starts. So you can continuously traverse the first curve to the terminal point of the second curve, and then this entire curve can be defined as or is defined as C1 plus C2. So you can have as well like this and then like this. Okay. So this is C1 and then this is C2. So this is curve C1 and this is C2. Okay. This is initial point of C1, terminal point of C1, which is initial point of C2, and this is terminal point of C2. Now from this to this, okay. So this point may be Z1, Z2, Z3, Z1, Z2, Z3. So Z1 to Z3, that is C1 plus C2, okay. That is C1 plus C2. All this will be required when we define integral of f over C. So when it will come integral of f over C1 plus C2, the curve C1 plus C2, it will be integral over C1 plus integral over C2. So those properties we want to do later. Integral over minus C will be minus of integral over C. Integral over C1 plus C2 is integral like that it will be. Therefore I have defined these curves first, okay, this negative of a curve, addition of a curve and so on. Now the next concept is length of a curve, which you have already done actually. Arc length formula you have done, but it is written in the complex notation here. That is, suppose zt is the contour, then the length of C, okay. So suppose this is interval AB of parameterization and you have curve in the complex plane like this. So this is ZA, this is suppose ZB, and then for any point T you have ZT on this, okay. So this is the function ZT, okay. Then integral mod Z prime T dt is called length of this. So integral from A to B mod of Z prime T dt is called length of C, is denoted by L. So length of C, this curve C. So length of this curve is defined like this, mod of Z dash. So this parameterization function we will have, so we find its derivative, take absolute value. So if you remember your first year BSc formula, it is x dash square plus y dash square square root. Exactly it is like this. Modulus means what? This is xt plus I times yt, derivative will be x dash t plus I times y dash t, and then modulus means x dash t square plus y dash t square square root. So same formula, but it is written in the form of a complex function, complex valued function. But if you take, you have taken modulus, so this is a real quantity anyways. So length is a positive real number because this is a positive and an integral of a positive function. So it's a positive real number. Length of the curve, arc length, okay. You are already familiar with that. Okay. And the property that is written there, that if phi is a continuously differentiable function which maps CD onto AB with phi dash u positive, then Z phi u is another parameterization of C on the interval CD, and under this reparameterization the length of C remains invariant. So let me explain this. This is another point. So you read this point 15 which I will explain to you again. Okay. So see, this is now this picture you have to keep in mind. So this is our curve C, okay, this is curve C. Now this is interval AB and this is parameterization ZT. So this point is what? Initial point, that is ZA. This point is terminal point, that is ZB, and as T moves from A to B, the points are traversed on this curve. That is our idea of parameterization. Now this function phi is on this interval CD, so this function is phi, which maps CD onto AB, and phi dash is positive. So this parameter let us denote by u, so phi dash u is always positive. Now phi dash is positive means phi is increasing. So as why it is taken like this? Because phi C is suppose A, then these points move in this increasing manner, then they will traverse this point here. Okay. Alright. Now I can apply phi on this ZT because ZT is a function on AB. Okay. So I can consider phi of ZT. Okay. Alright. So it is the other way around. Z of phi u, like that. It is Z of phi u. So I will take u, via phi I will go here and then apply Z. So it is just a composition. I will take u here on interval CD, apply phi and then you go here. Then you have your original function Z, but then that maps to on the curve. So u is now parameterizing this curve. So this curve is now parameterized on the other interval CD, because finally now what we have, Z of phi u and C less than or equal to u less than or equal to d, that is as u varies in CD, these points on the curve vary. So it has another parameter u now, and that varies in another interval CD. So it had original parameterization on interval AB, which is ZT. Now I can call this as function as WU on what? CD. Same curve, but different parameterization. Okay. Then the property is that the length of the curve is invariant. The length of the curve remains invariant. That is, whatever is the length, it is intrinsic property of the curve. Whether you traverse points by using interval CD or AB, length will not change. That is what is written here. That under this reparameterization, length of C remains invariant. Okay. So if you consider the formula for the length, then length is defined as Z dash T. Now that will be same as W dash U. So if you consider mod of W dash U integral, okay, from C to D, du, okay, all right, then that is same as mod of Z dash T. Is this clear why it is so? Because you put T equal to phi u in mod Z dash T. So if you have suppose A to B mod Z dash T dt, then that is same as C to D mod W dash U du, where W is this. Why it is so? Because you put T equal to phi u, then this is phi dash u du. Okay. So Z prime of phi u into phi dash u du, but that is same as Z prime of phi u into phi dash u du is W prime. So these two will be equal. Let me repeat again, that if you have this integral A to B mod Z prime T dt, which is actually length, this is definition of length. We have just now defined length of the curve. It's same curve, okay, but it has different parameterization, one in terms of u, other in terms of t. But what we are proving is that the length will remain same whether you parameterize by interval on interval AB or CD, or by a parameter t or by u, by the function zt or wu. It will remain same, length will remain same. That is what is proved here, because this is definition of length. Now you put, just see here and concentrate, t equal to phi u, then z prime t phi u, okay. Now what will be z prime of phi u? It will be z prime of phi u into phi prime, okay. If you put here t equal to phi u in zt, then z prime phi u into phi prime u you will get here, okay. What will be z prime of t, and when t is phi u, it is z prime of phi u into phi prime u, okay. But what is z prime of phi u into phi prime of u? It is exactly w prime u, okay. And t equal to whatever, t equal to a, then u equal to c, and t equal to b, then this is c. So this will get converted to c to d. So these two integrals are equal, means length remains invariant. Length of a curve is invariant under reparameterization. Okay. And further, if you take integral from a to b, so if there are two parameterization, so integral of a function, say let us write ft dt from a to b, if you take t equal to phi u, then it is c to d f of phi u into phi dash u du. Now example 16 represents this, illustrates this point. This point 16, one example is given. The example which illustrates the idea of a reparameterization of a curve. So let us consider this. So consider a curve C given by zt equal to 2 e raised to it. It is written there on your screen. Okay. So let us consider it here on this board. So what is 2 e raised to it? 2 e raised to it is a circle with center at origin and radius 2, because mod of zt is 2. Okay. So but then it is from minus pi by 2 to pi by 2. It is from minus pi by 2 to pi by 2. So this is right half of the circle with center at origin and radius 2. So let us consider this function zt equal to 2 e raised to it and minus pi by 2 less than or equal to t less than or equal to pi by 2. Let us see what curve it gives. So this is the parameterization of a circle, it is written there, but let us see this. So if you put minus pi by 2, see this is, so z of minus pi by 2 is equal to what? 2 e raised to I times minus pi by 2. That is 2 times cos pi by 2 minus I sin pi by 2. But cos pi by 2 is 0. This is 1, so it is minus I. So it is this point. Similarly, if you take, so this is minus I, this will be plus I. If you take pi by 2, it will be plus I. And then mod of this is 2. So this represents circle with center at origin radius 2, but only this part. So it will be this part. This is 1 suppose. Alright, and this is 2, then it is like this. Okay, minus I. So this circle is taken. And it is traversed from this minus pi by 2 to pi by 2. So it is like this, anti-clockwise. So this is circle with center at origin, okay, and it is not, it is from, so let us see, 2 times this, so 2i, it should be 2i and minus 2i. And this is 2, this is 2, this is 1. Here it will be I, here is minus I. Okay, like that it is. So it is circle with center at origin radius 2, like this. So this is the curve zt. Alright. Now one can have a reparameterization of this curve. One can have a reparameterization of the curve. The function wu defined on minus 2 to 2. So now consider the function, another function wu, which is equal to root of 4 minus u square plus I times u defined on minus 2 to 2, on minus 2 to 2. Now again you try to put, so can you see both this on your screen? So this function, if I put minus 2 here, okay, you get 0 as real part and minus 2 as imaginary part, that is exactly this point you get. If you put u equal to 2, you get 0 here and 2i, that is exactly this point you get. Clear? So, and if you square this, that is 4 minus u square plus u square, that is 4. So x square plus y square equal to 4. That means you get circle with center at origin radius 2. So it is same part that is covered. So this is another parameterization. this is another parameterization of the same curve. So this is a reparameterization of the curve C, this curve C, reparameterization. Okay. Now actually it is given there that in fact the function phi u equal to tan inverse u upon 4 minus u square gives reparameterization. That is, if you consider the function phi u is equal to tan inverse u upon root 4 minus u square. So this function, if you take on minus 2 to 2, then this maps minus 2 to 2 to minus pi by 2 to pi by 2. Is this clear? So this phi u maps, so minus pi by 2, minus 2 to 2 to minus pi by 2 to pi by 2, okay, and then to the complex plane where actually the curve is traversed. Like that it is. This function is 2 e raised to it, which is given by zt, which is given by zt, 2 e raised to it, on minus pi by 2 to pi by 2. Whereas phi, if you take this function, you can later on verify that if you put here minus 2, so minus 2, infinity, minus infinity, it will go to minus pi by 2, plus 2, minus, plus pi by 2. So it goes to minus pi by 2 to pi by 2 actually. And then this is also a parameterization and this is also a parameterization. Okay. There are two parameterization, but that is all right, that is fine. A function may be parameterized in variety of ways, but a reparameterization will not change the length of the curve. Okay. So that is what the idea of reparameterization is. Is this clear? That I have shown that this curve can be parameterized in two ways. And then this is intertwining function which will take you to one parameter interval to the other parameter interval. Now point number 17, that let fz be analytic in the domain D and let C be the curve, smooth curve in D given by zt. If Wt is f of zt, then show that W dash t is f dash zt into z dash t. Okay. So this let us prove. Okay. So what is given? Fz is analytic in the domain D. Now you have a complex valued function of a complex variable. So which is from D to C, where D is a domain in C. Domain in C. That means what? It is open and connected. So then you have this function f which is analytic. So f is analytic. Do you remember what analytic means? Do you remember what analytic means? Just recall what analytic means. So I want you to recall the definition of an analytic function. Okay. Function is analytic if what? In a domain D, if it is differentiable in the neighborhood of every point in the neighborhood of a point. Analytic at z0 means differentiable at every point in the neighborhood of z0. That is analytic. Or if you take an open set, then you say that it is differentiable everywhere in that open set. Then it is analytic. Okay. And then we know that f is analytic, then real and imaginary parts of f are all differentiable functions and they satisfy Cauchy-Riemann equations. So we have seen all that in detail in the previous chapter. Okay. So this is given that the function f is analytic. Okay. All right. And suppose C smooth curve in D given by Zt. So now some curve is given. So suppose Zt is the curve given on A to B, A less than or equal to T less than or equal to B. Then, so this is curve C. So as I am repeatedly telling, every curve is given by a certain function which is actually the parameterization of that curve, and that parameterization comes on certain parameter interval. Okay. So this is some function of T, complex valued function. That means these points are on the plane. So they traverse the curve. That curve is denoted by C. Okay. I hope this pattern you follow. That this is a curve, that means that this is in the plane. The points are given by Zt, so Zt is some xt plus Iyt, so these are complex number, points in the plane. But T varies in the interval. Okay. So as T varies in the interval, Zt varies on the curve. Alright. Now suppose Wt is f of Zt. Wt is f of Zt. That means what you see this picture. So suppose this is domain D and this is a curve in the domain D. So this is a curve suppose in domain D. So these points are Zt actually. Alright. So let me draw this picture here on the other board. I will draw this again. So see this very carefully. This is most important. So this is parameter interval, say AB, okay. Then this is points T vary in this. Okay, so let me take a variable point, say T. Can you see this T? Okay. So now in the plane, complex plane, you have the curve. Okay. Now this is domain of the function f. So this is D, and the function f is from C to C. The function f is from C to C, whose domain is D, and the curve lies in D. So this is function z, so zt. So za is this point, zb is this point, and as t varies, so this is picture. Now f will act on these points because this curve is in the domain of f. So this is D, at every point of D, f can act and produce a complex number. In particular, it will act on zt. So we will have f of zt, f of zt. So f of zt I define as a function now on interval AB. So that is defined as Wt. So Wt is defined on interval AB as f of zt. So it's a composite function. First here and then here. Okay. We know how to find derivative of a composite function. So we will apply that now and find W dash t. So is this clear? W is from AB to C, which is composition of Z and F. Okay. Is this clear? So suppose let us write. So can you want to try for 2 minutes? So this is nothing but composition of F and Z, and now we want to apply chain rule to find W dash. Okay. So just try for 2 minutes. Let me give you 2-3 free minutes so that I will not talk, and you try this. You show that W prime t, so show that W dash t is F prime Zt into Z prime t. Okay. Try to show this. Okay, so let me start. So I said that you try, but then, okay, I gave you 1 minute and we want to move ahead. So let us write fz as uxy. So suppose as usual let us write fz as uxy plus I times vxy. Okay. And zt as xt plus I times yt. xt plus I times yt. Because this is a function of t, so it has real part xt, imaginary part yt. Then wt is what? By definition, wt is f of zt. So in place of z, you have to substitute zt. That means in place of xy, you have to put xtyt. So it is equal to u of xtyt plus I times v of xtyt. U of xtyt plus I times v of xtyt. Now what is w prime t? So w prime t is equal to, how to find derivative of this now? It is u prime of this plus I times v prime. Okay. But u is a function of x. Okay. So it is equal to, u is a function of x and x is a function of t. So it is dou by u by dou by x into x prime t dx by dt. Okay. Plus dou by u by dou by y into y prime t, because y is function of t. So this is derivative of the real part. So dou by u by dou by x into x prime plus dou by u, this is our usual chain rule, plus I times similarly dou by v by dou by x into x prime t plus dou by v by dou by y into y prime. Now here we use that f is analytic. So as f is analytic, it satisfies Cauchy-Riemann equations. So I will substitute Cauchy-Riemann equations here. So dou by u by dou by x is equal to dou by v by dou by y. Okay. So I will substitute this dou by v by dou by y by dou by u by dou by x. So w prime t is on the left hand side. W prime t is dou by u by dou by x, x dash, dou by u by dou by x into x dash. So I am dropping this x dash t, this means x dash t, plus I times dou by u by dou by x I will write again, because this dou by v by dou by y I will replace. So plus I times dou by u by dou by x into again into y dash. So this is one term which I have written these two terms. These two terms I have written because del by u, see again, del by u by del by x into x prime I have written, and del by v by del by y I have replaced by del by u by del by x, y prime. Now del by u by del by y, so plus del by u by del by y, y prime minus I times, because del by v by del by x is minus del by u by del by y. So minus I times del by u by del by y into x prime. Okay. So you get that it is equal to, so if you take del by u by del by x outside from this, so del by u by del by x into bracket x prime plus I times y prime, okay, plus I into, if I take I outside, del by u by del by y outside if I take, then, so if I take this minus I outside, x prime minus plus I times y prime, because this term, you read this, minus I into I is plus 1. So this is del by u by del by y, y prime term I have written here. Okay. So this is del by u by del by x minus I del by u by del by y into x prime plus I times y prime. But this is nothing but f dash. This is nothing but f dash. So this is f dash in zt into, this is z prime, because zt is xt plus I times yt. So this is z prime t. So that is what we wanted to prove. Okay. So this is exercise in Churchill. I hope you have written it down. If not, you may take down. Here you need to use Cauchy-Riemann equations, and this property is used in integration. So this w prime t is f prime zt into z prime t. See, remember this u is a function of xt now. So this del by u by del by x, this is all evaluated at zt. Okay. All right. Now let us turn our attention to contour integration. Okay. So let us take a pause and review what we have done in the complex integration. We first defined a complex valued function of a real variable t, that is wt ut plus I times vt. Then we defined the derivative of such function, that is w dash t is equal to u dash t plus I times v dash t. Then we defined integral of wt as integral ut plus I times integral vt. And then we saw that all the properties of standard differentiation and integrations are satisfied. Whenever they are not satisfied, I have pointed out. So for example, differential calculus, this mean value theorem does not hold. Integral calculus, mean value theorem for integration does not hold. And we gave examples like that. But then addition, multiplication, scalar multiplication, chain rule, all the properties hold for differentiation and integration of complex valued function of a real variable t, that is function of the type wt equal to ut plus I times vt. That was our first section. In the second section, we defined curves. So curve we defined as a function zt, xt plus I times yt, t varying in certain interval ab, and zt is a continuous function, means this xt and yt are continuous. And then this zt is called parametrization of the curve on an interval ab. So if zt is defined on interval AB, then the curve C, the points are ZT, but they are parameterized. T is varying in AB. So we saw examples like that. That is, T is varying on 0 to 2 pi, T is varying on minus pi by 2 to pi by 2, T is varying on minus 1 to 1, T is varying on 0 to 1, T is varying from minus 2 to 2. So many examples we saw of curves. That is all about the parameterization of a curve. That means you take an interval. On that interval, if you vary the points continuously, you are tracing the points on the curve of a complex curve in the complex plane. Okay. So that is how we define curve. A piecewise smooth curve is called a contour. So that word should be properly interpreted, that it has only finitely many points at which the derivative is not continuous. Otherwise it is smooth everywhere. And then we define addition of two curves, negative of a curve, length of the curve, reparameterization of the curve. All these properties of curve we have defined in the second section. In the notes given to you, I have clearly written all these points. So I suggest you that you please go through all the points again after you go back. I have solved examples on the integration in these notes. You open the Churchill's book and also see the examples solved by Churchill. I have solved problems purposefully from exercise so that you can read problems from the Churchill which he has solved and read problems in the notes which I have solved. So you have more number of solved problems now, and then you solve some problems. There is no way out. You have to solve problems. Try to understand the concept and solve the problems. So this is exactly what we have done so far in complex integration. And now we are about to begin what exactly contour integration means. So that is the crux of the matter. Integral of f over a curve C means what? So let us start contour integration, okay? So it is right there in front of you on your notes. Can you see contour integration? Yes. So let us see what we want to do. So now we have a function f on a domain D in the complex plane to C, where D is a domain. So you have to first understand the situation. A function is given to you which is to be integrated. Is this clear? We want to integrate this function. Now we integrate on what? Like in case of Riemann integration, we integrate on AB, a real function. This is not real, this is complex valued function defined on domain D. So the domain D will be something like this, suppose. And here you have complex plane. Okay? Now you want to integrate this function. But over what? On what? Like here it was on interval. Here what do you want to take? So here you want to integrate on a contour. So we want to integrate a complex valued function of a complex variable, function of a complex variable on a contour C in the domain. So this sentence you have to read again and again. This is what we want to do. There is a function, and in the domain of the function there is a contour, and we want to integrate this function on this contour. Now what does this mean? What do we mean by that? We will define. That is what exactly we want to define. That is exactly what we are going to define. What do we mean by integration of this function on this contour? And we already know now this contour means what? This contour means it has some parameterization. So there will be some interval, and t as varies, these points will be zt, and this point will be initial point za, and this point will be terminal point zb, and as t varies here, you will have zt. So suppose this is, let me orient this curve like this. And this function is defined everywhere on this plane, but we want to integrate on this contour. That definition I will give now. So you read this sentence again. Or equivalently, you may read the first sentence in this section on complex contour integration. Read that. In this section, we define the integral of a complex valued function of a complex variable defined on the contours in the complex plane. Okay. Now, how do we define? That is given there in the next page, on the next page. Okay. Next page. Suppose the contour C is given by the function zt, as I have written it here. So this function which gives this contour is zt, suppose. Corresponding to every contour, there is a function zt, which is parameterization of that contour on certain interval on the real line, say AB. So please understand this, that when a contour is given to you in the complex plane, means some function zt is given to you and some interval is given to you. So that function and this interval is used to define this integral, remember. So C is given by the function zt, the function, let f be the function which is piecewise continuous on C. So for integral to exist, this assumption is made. So suppose this is piecewise continuous, function f is piecewise continuous on C. You may initially think of a continuous function only, forget about piecewise and all that. Suppose f is a continuous function on all points of the curve C. Now comes the important statement. The integral of f on C, denoted by integral fz dz on C, is defined as integral fz dz over C is equal to a to b f of zt into z prime t dt. So remember, right hand side is integral over interval ab of a function what? Complex valued function of real variable. That was our starting point of this chapter. So see the right hand side, f of zt, f is from C to C. Okay, so f of zt will be a complex number, and z prime t, zt is also complex. So this inside thing varies on t, so it is a function of variable t, but it is complex valued. So f of zt into z prime t, see on your screen. So the definition of contour integration is integral of f over contour C is integral from a to b f of zt into z prime t dt. Now I hope our camera shows the entire formula here. Yes? Integral f over C along with this figure. Can you show this figure and this formula I want? Okay. So integral of f over C, integral of a function over curve C is f of zt. What is zt? It is parameterization of this curve C. Z prime t, zt is suppose ut plus I times vt, then z prime t is u prime t plus I times. That we have all done now. All hard work is already done. We have defined what a contour means, we know what parameterization means, we know how to find z prime t. What are a and b? The zt is defined on the parameter interval ab. So this contour integration finally turns out to be integral on a certain real interval of a complex valued function of a real variable t. Let me repeat my sentence. This side, everything is in a way complex. This curve is in the complex plane. F is from C to C. So this is contour integration. Function f, show this figure. So this function f from C to C, and this contour is in the complex plane, and we are integrating on this contour. But this contour is given by a parameter interval AB and a function zt which parameterizes this curve. So zt takes all these values actually as t varies. So we transfer this here, okay, that the integral of f is written in terms of integral over AB. See here, integral over AB, which is the parameter interval, into z prime t dt, f of zt into z prime t dt. So f takes values on the curve because zt are points on the curve, and fzt means f is taking only points on the curve. So actually what is varying is only t. So we are using integral dt, that is over a to b. But if you put f of zt to multiply by z prime t dt. So this is definition. Now you have to read this definition 2-3 times. So you read this. Integral of a function f over a contour C is integral from a to b, where a to b is parameter interval of the contour C. F of zt, f is given function, zt is parameterization of the curve C, and z prime t we can find once we know the zt. So this is what the definition is. So read the comments immediately after the definition on your screen, white screen, notes. That note that the right hand side of the equation above is an integral of a complex valued function of a real variable t on the interval AB, and we know how to evaluate such an integral. This integral is some function of t but complex valued. So this entire thing we will be able to write as ut plus I times vt, and then we have defined this integral as integral of this plus I times integral of this. So when you know f, when you know z, you can find this entire thing and express it as ut plus I vt, and then integrate this plus I times integral this. That is what is written there. And immediately I have given you an example so that you will understand this. So read that fz equal to z plus 2 upon z. This is again from the exercise of Churchill's book, so that you read the solved problems from Churchill and now you can read this also. So the function is given and a curve is given. So for contour integration, two things will be given to you. Function to be integrated, that is integrand, and the contour on which function is to be integrated. So that curve given here is semicircle, 2 e raised to I theta. Okay. So I will draw the picture if you want. So let us do this example now. Let us do this example. That is, what is function? Function is given and a contour is given, and we want to do this contour integration. So what is function given? Function given is z plus 2 upon z. Fz equal to z plus 2 upon z. This is function. What is contour given? Semicircle 2 e raised to I theta. So C is semicircle 2 e raised to I theta. So what is parameter interval? 0 less than or equal to theta less than or equal to pi. So let me draw this contour. Theta equal to 0, that means 2. So it is like this. This is 1, this is 2 suppose. Theta equal to pi, e raised to I pi, that is minus 1, so minus 2. And mod of this, mod of e raised to I theta is 1, so mod of this is 2. So all points are on the mod z equal to 2. So it is a semicircle like this. So it is this semicircle. So this semicircle is the contour on which we want to integrate, and this is the function to be integrated. So we want to find integral f or c. Now everything we have z theta, that is the function which parameterizes this curve, parameter interval we have, function we have, and definition of the integral we have. So what is problem? We find out the integral now. So integral of f or c, this contour I denote by c, okay. So integral of f or c is a to b, but what does a to b means what? Parameter interval. So here parameter interval is what? 0 to pi. So it will be 0 to pi f of z theta. Now variable is theta. You may call theta, u, pi, t, whatever. So here theta is used. So f of z theta. See the definition. F of that on white screen you can see on your notes. F of z theta into z prime theta. F of z theta into z prime theta d theta. That is equal to, now this is f and this is z theta. Okay, this function is z theta. This z theta you want to put in f, that means f of z theta. So in place of z, z theta will come. So 2 e raised to I theta, 2 e raised to I theta plus 2 upon 2 e raised to I theta into z prime theta. What is z prime theta? Z prime theta is 2I e raised to I theta. 2I e raised to I theta, because z theta is this. So derivative is 2I e raised to I theta. Is this clear? And 0 to pi d theta. So e raised to I theta will get cancelled, 2 will get cancelled. So it is I times this. Okay. So it is evaluated there. 2I e raised to I theta plus 2. So you can just take this 2I outside. 2I 0 to pi. 2I, have you understood? This 2, and this I is outside. So it is 1 plus e raised to I theta now. 1 plus e raised to I theta d theta. Zero to pi. Okay. So 2I e raised to, thus now this is 0 to pi, 2I outside, 1 plus I e raised to I theta. So now you integrate this. This integral 1 is theta. So theta from 0 to pi. That means pi. Is this clear? Theta. And e raised to I theta integral is what? So 2I I have written again, e raised to I theta upon I. 0 to pi. So 2 pi I plus, it is written on the next page, these computations are carried out, you can read that. So it is 2 times, so this is 2 pi I, this is 2 pi I plus this I will get cancelled, 2 times e raised to I pi minus e raised to 0. So e raised to I pi is minus 1 and minus 1. E raised to 0 is 1, but this lower limit. So it is minus 4 plus 2 pi I. So it is minus 4 plus 2 pi I. You see this answer? You check this. Okay. Alright, you can read the next problem also. That is also illustration of how contour integration is carried out. So you can read the next example. Time today is over, but then I suggest that you read entire chapter on integration before the next lecture, and then read what I have written further also. You may read next example, how the contour integration is carried out, and try some problems from the Churchill's book. Okay. The next lecture will be on Friday instead of Saturday. It is shifted to Friday. Okay. Okay. Till then, goodbye.